Hi, this is Cameron Bennett, and I'm going to be discussing and going over the problem on the website. So, first of all, why is this problem important? I think it's important because understanding the heritability of specific human traits is important for understanding how disease progresses through families, as well as other particular heritable traits, whether they might be disease or non-disease, such as the red-haired genotype. So I decided to choose this problem because I wanted to understand how red hair is transmitted through families. So, I'm a redhead and I'm one of the only redheads in my family. So I wanted to have a problem that would demonstrate how red hair is inherited through families and how relatively rare it is. So the start of our problem is a pedigree. As you can see, we have 4 generations with 4 individuals. The first part of this problem is identifying the genotypes throughout this pedigree. So I think the best way to start is to look at our affected individuals. Because this particular gene is heritable in a autosomal recessive fashion, we know that our affected individuals are going to be 2 lowercase r's. Because of that, we know that the parents of those individuals, because they're non-affected, are going to be a little r and a big R. So I'm going to go through and put those in. So that's what we have so far. We know that for individuals that were able to receive an R, or a small r allele, they're going to have a parent that has at least one. And then we can also know that it generally follows through generations. So we know that because this individual that's affected has this individual that's also affected as a descendant, this gene most likely came from this individual. So looking at that, we've pretty solidly established who has a heterozygote genotype versus who has a homozygous genotype. At this point, it's going to be pretty difficult to determine who is heterozygous and who is homozygous. So we're going to have to basically put everyone else as an R and then a dash, because we can identify it based off of the fact that they are not affected, that they're going to have at least one dominant allele. But because we don't necessarily know everything about them and we can't tell based off of their children, we can't necessarily and definitively say whether or not they have a homozygous or heterozygous positive allele genotype. So that's the first part of this problem. In the second part of this problem, we look at individual 3-3, which is a homozygous recessive individual, being crossed with a heterozygous carrier of this particular gene of interest. That would result in our cross being big R, little r versus little r, little r. This particular trait is Mendelian, so we could cross it in a Punnett square. In our Punnett square, we would set it up as R, big R, little r, and little r, little r. When we cross them, we have big R, little r, big R, little r, little r, little r, and little r, little r. That gives us a ratio of 2 big R, little r to 2 little r, and thus 2 non-red to 2 red. That means that 50% of their children will have red hair. The final step of this problem is the most complicated because it asks us to determine the probability that these above individuals will have 5 children, or given that they have 5 children, 2 of those children will be both female and have red hair. I decided to go with this combination because from the research that we found on the topic, most anesthetic issues of efficiency are specific to women with red hair. So I wanted to explore the probability of having children who are women who, because they are women and also have red hair, will have issues with anesthetics. So we're going to have to use the binomial expansion equation for this problem. So to start off with, we need to determine our probability of everything that's not going to be a redheaded girl. So we want to look for the probability of a redheaded boy, a probability of a non-redheaded boy, and the probability of a non-redheaded girl. So this is pretty basic. We don't necessarily get into our binomial expansion yet. We know that the probability of having a redheaded child is 1/2, and because it's an and here, we multiply this, and the probability of having a boy is also 1/2. This is 0.25. The same follows for the rest of these. 1/2 chance of not being redheaded times 1/2 chance of being a boy, and then the 1/2 chance of it being a non-redheaded girl times 1/2 chance of being a girl, 0.25. So now we sum all of these to be all of our options that is not our ideal goal of the redhead and a girl, so 0.75. This leads us to the knowledge that 0.25 is our probability of having a girl who is also redheaded. So now that we have our ratios of things that are and things that are not, we can go into our binomial expansion. So we start off with the number of total events. In this case, it's 5 children, so 5 factorial over the number of individuals in one event. So we want 2 redheaded girls, so 2 factorial, and then 3 individuals that are not redheaded and also not girls, so 3 factorial. Our first one we want to know for how many of our redheaded girls. We know that's a 2.25, so 0.25 to the power of how many people are in that event, so 2 times 0.75, the probability of everything that's not a redheaded girl, times the number of events that are not a redheaded girl. So when we put this into our calculator, we're going to come up with an answer of 0.264. So that is the answer for this problem.